Hi everyone, my name is Christopher and today I'm going to present my work on affordable graph neural network framework using topological graph construction. This work is done at Basira Lab, Imperial X, and is supervised by Dr. Islam Raki. First, what is GNNs or graph neural networks? GNNs are a recent variation of neural networks that are designed to handle graph-based data. First, we have the tabular datasets, which are used by the traditional neural networks, and samples here are independent of each other. Then, we have the image datasets for convolutional neural networks for computer vision applications, and here, samples or pixels are placed in an Euclidean space and are connected to adjacent pixels. Finally, we have the graph datasets for GNNs, where samples or node connectivities can be arbitrarily defined. With the advent of GNNs, neural networks are much more accessible and is used in many new practical applications involving graph datasets, such as network neuroscience, fraud detection, drug discovery, traffic forecasting, and retail recommendation. However, GNN comes with scalability issues. First, GNN requires much higher GPU memory footprint compared to standard neural network, and this is contributed by the aggregation operations in each layers. Secondly, this aggregation phase causes sample to be interconnected and makes mini-batching non-trivial. This causes neighborhood explosion, which I will explain later. Finally, many GNN applications will involve large and complex datasets, which can scale to millions of nodes. For example, graph convolutional network, which is also one of the earliest and simplest GNN model. In GCN, sample interconnectivity causes sample to be dependent on each other, and on ECN layer itself is going to consist of two phases, aggregation and transformation. Aggregation is the process of aggregating adjacent node embeddings, whilst transformation is the process of transforming the embeddings through weight multiplication. Here, an example of two-layer GCN, and we can see that the A is going to be the normalized JCC matrix, and when we multiply A and X, it's essentially going to be aggregating the neighboring embeddings. Whilst multiplication with W is going to be the transformation phase itself. Here we visualize the computation path of two-layer GCN, and as we can see, to compute the embeddings at the hidden channels, we need to have the information of the adjacent nodes embeddings at the previous layers. Hence, we can see the sample interconnectivity impact on the computation path. This dependency leads to neighborhood explosion, which makes mini-batching non-trivial. This is because in naive mini-batching, we need to add an additional one-hop neighborhood of nodes for every layers we have, leading to exponential time and memory complexity. This is visualized in this figure. For example, we want to set these four nodes as our mini-batch. For a one-layer GCN, we need to add these one-hop neighborhoods, whilst if we have two-layer GCN, we need to add another hop neighborhood, the second hop neighborhood. Hence, we see that we need much more supporting nodes compared to the mini-batch itself, even only for two-layer GCN. Therefore, to democratize GNN training, we are proposing a three-stage memory-efficient GNN training framework using novel centrality-based construction. Our framework will consist of the input graph reduction, where we will use our novel centrality-based construction itself. Then it will be followed by the mini-batch construction stage, here as is shown and will be discussed later. And then we also have the layer compression stage. And finally, we're going to name our framework the CQ sign, which is short for the contracted quantized sign model. First, let's talk about the graph reduction stage. Here, we're proposing a novel centrality-based edge contraction scheme to reduce the input graph. The centrality measure itself is a classical way of quantifying nodes' topological importance and is usually defined by their hopness or how well they perform as a hop for other nodes to connect. Hence, we can simply preserve only the most important nodes based on the centrality values. Here, edge contraction is also used to avoid graph fragmentation, which is visualized in this figure. For example, we want to remove this node and we want to contract it with using this edge. Here we can see that the results will be like this. And here the connectivities between the graphs is going to be maintained, and we want to add another component. whilst if we're using direct node removal, there's a chance that we might fragment the graph into two separate components, which we don't want. And this whole process is visualized in this flowchart. First, we have the input graph. Then we compute the centrality measures. Then we can reduce the graph by preserving only the most important nodes. Next, regarding the centrality measure itself, we experimented with the following centrality measures. First, the degree centrality, which is essentially the degree or number of edges connecting the node. Next, closeness centrality, which corresponds to how close the node is to every other node in the graph. Then we also experiment with the betweenness centrality, which is basically the number of node pair shortest paths that crosses our node of interest. Then we also have the PageRank centrality, which was originally developed by Google to rank their websites. And finally, we have the eigenvector centrality, which is an improvement to the degree centrality as it now considers both degree and neighbors quality. Next, for the MiniB construction stage, here we're going to use SIGN model, which decouples the aggregation and transformation phase of GCN. SIGN is visualized in this figure, and as we can see, it first consists of the initial aggregation phase, which consists of concatenation of various power matrix aggregation, and this is also shown in our flowchart. So first we compute the aggregation of various power matrix before concatenating it together. Then it's going to be followed by a transformation phase, which is essentially MLP training. This is also shown in our flowchart as follows. Finally, we have the layer compression stage. Here we incorporate the 2-bit activation quantization scheme by ACTNN, and we chose to quantize the activation because it is the major memory contributor in GNN, since it is directly proportional to the graph size. The quantization itself is visualized in this figure, which we show that the cache activation are being quantized first into 2-bit precisions before finally being dequantized again back to the full precision to be used for the backpropagation process. This is also shown in the flowchart as follows. And moving on to experiments, we evaluate our method using PPI dataset and then the MAT-MNIST organ datasets. PPI is the protein-protein interaction datasets, while the MAT-MNIST organ is image graphs of liver tumors. The hyperparameters used in the experiments is as follows. And here, layers and heated units are set sufficiently high in order to mimic heavy and resource-intensive GNN training and to show the impact of our method. Now, how to determine the optimum node budget for our graph contraction? To do this, we can plot the validation accuracy of contraction on various node budget and use the convergence point. As we can see, these plots show that convergence is achieved at relatively low node budgets, and this implies the high contraction potential of our datasets. From the plot, we get these following results on the node convergence points, which is roughly equals to 33% of the whole graph for PPI and only 57% for organ datasets. Next, using this node budget, we compare the testset prediction accuracy and GPU memory efficiency. Our first finding is that depending on the centrality measure being used, our contraction can achieve very similar performance to the original graph. For example, on PPI, we can see that eigenvector centrality, or EC for short, is able to achieve very similar performance compared to full graph training. Hence, the choice of centrality needs to be treated as a hyperparameter, as different datasets can perform differently depending on the centrality measure being used. Secondly, we can see that our contraction method can significantly reduce the training memory footprint across all benchmark models. For example, using contraction on GCN, so we have GCN and CGCN here, stands for the constructed GCN, we can see a reduction of up to 66% in terms of memory usage on PPI on GCN with PPI dataset. Finally, we show that our proposed 3-stage framework, CQCN, is able to achieve the lowest memory footprint across all benchmark models, while still, of course, maintaining very competitive accuracies, which is shown in this figure. The memory usage difference is also very significant. We can see that CQCN using only 97% less memory than GCN. And That is all for my presentation today. Thank you so much for your attention, and for more, please visit us at Basira Labs website.